All right. Good afternoon, everyone. Welcome to the session 23, Evaluation Methods of IEEE VR 2020. Let me introduce myself. I'm Janki Dodia, and I will be chairing the session today. Before I begin the session, some important points. After each presentation, which will be for around 15 minutes, we will have 3 minutes for taking the questions. You can send your questions using the Slido at slido.com with the code IEEE 2020, that's in capital. And people can post their questions on the Slido, and we'll take them during the question and answer sessions. Okay, moving on to our first speaker. Our first speaker is Tiara Feuchtner. She is a postdoctoral researcher at Aarhus University and a research coordinator for the Manufacturing Academy of Denmark. She will be talking about design and evaluation of a VR training simulation for pump maintenance based on a use case of Grundfos. Okay, over to you, Tiara.
Thank you very much, Janki. So this publication is based on the master thesis of my former students, Frederik Linoy and Kasper. And we present this design and evaluation of this VR training simulation for pump maintenance based on a use case at Grundfos. And in particular, we simulated a sequential maintenance task in which we replace an O-ring of a Grundfos dosing pump. We then evaluated this training simulation in comparison to 2 traditional training methods that are currently used at Grundfos. So as most of you probably know, many companies nowadays are interested in leveraging VR simulations for training of their workforce. And they often have a kind of checklist like this one to help them decide in what cases to opt for VR. So for example, if a task is easy to repeat, takes more than 5 minutes, has a linear workflow, is performed by more than 25 people, and there's a need for standardizing it for that reason, then they might assume that VR training has benefits in terms of efficiency and cost. However, this is not necessarily backed up by research. If we look at publications in this area, we find fairly mixed results, with some publications claiming that mixed reality training, including VR, is better than real-world training. Others saying that there's more or less an equal outcome between VR training and real-world training, and yet others say that actually VR training leads to worse outcomes. So obviously, these results depend strongly on the parameters that were evaluated, on the conditions that were compared, and the scenarios that were simulated. But aiming to find some clarity in our particular use case, we evaluated this training simulation in comparison to the 2 traditional training methods that are already used at Grundfos, namely pairwise training and video training. Now, before I talk about this evaluation that we did, I'd like to give you just a few details on the design and implementation of our VR simulation. So our system was implemented in Unity, and we used an HTC Vive headset and controllers for interaction. We acquired virtual representations of the tools and the pump components that need to be disassembled and reassembled in this maintenance task. So in VR, we had a needle tool and a torque wrench, as well as a CAD model of the pump, including all the separate components. And all of this was placed in a scene that resembles an industrial production floor to provide a believable environment for the scenario. Next, we needed to identify a discrete set of steps of this maintenance task. So we did this based on the job instruction video that you see here, which was provided to us by Grundfos. And based on this video, we identified 19 steps, starting with putting on the safety equipment, so gloves and glasses, and then disassembling the pump, exchanging the O-ring, which you see in step 10 and 11, and then reassembling all the parts. We provided the instructions for these steps as a written list that the user could refer to at any time. So it was placed on this tablet that was on the workbench. And for redundancy, we also played these instructions as voice recordings. Further, there was visual feedback in form of an animation of the virtual hand or virtual tools indicating proper movements. And we also had highlights for objects or object placeholders, which the user should focus on. So those are the yellow highlights that you see in these pictures. In terms of interaction, it was very important to us to go beyond a pointing and clicking interaction and instead teach users the realistic use of these tools as far as we could. So to show them the actual movements that they needed to perform during the task and also require these movements for interaction. But of course, the simulation lacked noticeable feedback that you would have in the real world. So you wouldn't notice the screw getting a bit harder to turn as you tightened it or moving in further. So we implemented artificial progress feedback, so this rotary feedback dial that you see here. And we also provided haptic and audio feedback, especially for this torque wrench. When you tightened it beyond torque, it would click like the real thing does. Similar to the realistic use of tools is the realistic handling of components, which we aim to enforce. So we wanted to avoid snapping of components into place as soon as they were held close enough to the pump. Because if we snapped, we realized that users didn't actually learn how to orient the part since they didn't need to pay attention to this. Instead, we require that the user orients the component correctly before the highlight actually turns green and they can let go of it. And thereby the user does actually learn to orient the components correctly. Then during pilot studies, we discovered that our simulation was not actually very effective. And there was a huge difference between just following the step-by-step instructions and actually learning the task. So basically, participants successfully finished the task, but they came away not remembering much afterwards. So we needed to actively challenge the users to reflect on their task. And to address this, we implemented a second level of difficulty. So on the first level, or beginner level, they got offered full guidance with all the features that you saw so far, so animations and highlights and everything. And then in a second or intermediate level, they got reduced guidance. So here they got the list of tasks on the tablet, and they still had the audio recordings, but no animations and no highlights. So in this example, participants had to figure out for themselves what the dosing head was and how to remove it, if you read that instruction there. So to evaluate our approach, we conducted a user study with 36 participants. These were mainly recruited on campus or through our social networks. We divided them into 3 groups. So we had 12 participants per training group. And after training, their performance was evaluated in doing the maintenance task on this physical pump setup with 3 pumps, actually. So they would do the task on one of these 3. As mentioned before, the 3 training types we compared were pairwise training and video-supported training, which are the 2 traditional training methods used at Grundfos currently, and also VR training, which is somewhat new to them. Now, in pairwise training, an instructor supervises a trainee doing the task, and the trainee thereby gains hands-on experience with the physical pump. Also has the chance to ask questions, and the instructor can thereby adjust the level of assistance he provides based on that. In video training, that was done with a pre-recorded video of the step-by-step process that we received from Grundfos. And the worker can follow this video while doing the task. That means the participant here also gains hands-on experience with the physical pump. And the participant can also pause and replay the video whenever needed. And finally, in our immersive VR simulation, participants trained independently, unaided by instructors. They received the step-by-step instructions on 2 levels of difficulty. So first with full guidance and then with diminished guidance. And they also received multisensory feedback. And maybe something I should add here, all training types, the training sessions were repeated twice. So not only just in the VR training. Further in the VR training, before they actually started with the training session, participants experienced an initial sandbox environment to get familiar with VR. So here they could learn the interaction techniques, learn the use of the tools, and learn to understand the types of hints or guidance that they received. Prior to the experiment, we hypothesized that VR training is effective for learning a structured maintenance task. That was our first hypothesis. Further, we thought that VR training and pairwise training would be comparable in terms of the task completion time and the number of errors that participants would perform afterwards. We also thought that video training would be, that VR training would be comparable to video training with regards to the same parameters. And finally, we hypothesized that people's confidence in actions would be higher after VR training than video training, because in VR training, they could learn in a 3D environment and explore this environment freely, whereas with video training, they would get all the information just from a 2D screen. And very often there were occlusions in the video. So that's what this hypothesis was based on. The procedure for the evaluation was as follows. First, participants gave their informed consents. We collected demographic information and information on prior experience with VR, as well as technical skills. Then they were shown the physical pump setup with the individual components and the tools they were going to use. And then came the training sessions, depending on their condition. And these were, as I mentioned earlier, repeated twice. After this followed a mental rotation task to diminish the recency knowledge effect. And that was followed by the evaluation of the task on the physical pump. The study then ended with a semi-structured interview and questionnaire. Now, the comparison of training types was based on performance in the evaluated maintenance task. And we chose completion time, number of errors, and level of confidence as measures for the performance. The following were our main findings from this evaluation. So, first of all 3 groups were capable of successfully completing the task after only 20 minutes of training. So any errors that were made were recovered from, and there were no complete breakdowns. So this lends support to our first hypothesis that VR training is indeed effective. However, if we then look at the task completion time, we can see that VR training led to significantly longer task completion times. On average, participants took about 1.6 times longer for the maintenance task after training in VR compared to the other 2 groups. So this does not lend support to our second and third hypotheses with regards to task completion time. Now, if we look at the number of errors, we see a similar pattern that in VR training, there were significantly more errors. So they made more than 3 errors on average, whereas in the other conditions, they made around 1 or even less. Again, this does not lend support to our second and third hypothesis, by which we assumed that these would be similar. And if we look at the level of confidence, this actually reflects the objective performance measures. So participants felt significantly less confident after VR training than both others. And confidence was evaluated by rating this item here, how confident were you in your actions, on a 5-point Likert scale. So from very, very unconfident to very confident. And this does not support our hypothesis 4. So to summarize, we can say that while VR training was effective, we have to concede that both other training types were superior. And we think that we underestimated how much importance hands-on experience actually has. So we think that this is at least in part due to the richness of real-world feedback. So I'd like to conclude by mentioning a couple of limitations of our research and potential directions for future work. So first of all, our participants were mainly recruited on campus, and it would, of course, be interesting to evaluate this with apprentice technicians or maybe Grundfos customers who actually buy this kind of pump. Further, we did not support hand tracking in this VR system. So participants could in particular not mimic these fine motoric interactions that were shown by these animations that you see at the top. That's a hand guiding you and showing you how you should be acting. But the actual interaction looked like the bottom image. So if you pulled the trigger, the hand would kind of just make this grabbing motion. And our future work will definitely include hand tracking to try to actually leverage this a bit more. Further, we think there should be richer multisensory cues, and future technological development might enable richer multisensory feedback to a degree where this might lessen the superiority of other hands-on experiences by simulating this better. Next, our VR training did not allow for trial and error. So you could not assemble something wrongly, realize the mistake later, and fix it. it simply wouldn't let you do a task if you picked the wrong component. Of course, if you're working on a pump, physical pump, you can actually do that, and you can learn by making mistakes. So this is something that we think would be interesting to explore further. We should also in future explore not having a predefined number of repetitions, but maybe instead have a repetition of trained test cycles, having people train to full proficiency and just count the number of cycles this requires. And of course, there needs to be further evaluation of how people's prior expertise may impact the usefulness of VR training, and what types of skills can actually be trained well in VR. So just to repeat the main findings, we found that VR training is effective. However, traditional approaches were superior. And we hope that with our insights and considerations, we can help people weigh the needs and requirements when debating the use of VR training, motivate training experts to consider VR maybe as a complementary training mode instead of a replacement. And further, we hope that we could highlight the importance of implementing different levels of difficulty and rich multisensory feedback. And that's all for me. I hope that you have many questions and would be happy to try and answer those. Thank you.
Thank you, Tiara. Okay, we will be taking questions now. They seem to have not appeared on my window for some reason, but so there's a question which says, how well do we think an expert mediated training in a social VR environment could be? There's something to be said for encouragement and positive feedback in hands-on training.
This is a very interesting question, and something that we actually also discussed with the people at Grundfos. So in particular, what if you had, an instructor in social VR? I'm thinking that's what the question's referring to, because then you could have this kind of pairwise training, but in VR, right? And I think that could be quite powerful, in particular because that also allows the instructor to adjust the level of help that he's giving based on the trainee's questions, right? So I think that would make things somewhat easier. However, we have the drawback that then we actually need an instructor to be present. And that's one of the reasons why the companies go to VR training in the first place, because they want to save the money and they want to be able to train multiple people at the same time without having to have this instructor there. I hope that answers the question.
Okay, all right. Thank you, Tiara. Another question is that what scale, there's an audience who wants to know what scale did you use to measure perceived efficacy? And did you consider the intrinsic motivation inventory scale to measure confidence and self-efficacy?
So no, the intrinsic motivation inventory scale wasn't used. Basically, we really just used this one item on a 5-point Likert scale. And in hindsight, we should have probably evaluated the subjective, the performance a bit more. The thing is that this was kind of added afterwards. So we just limited it to this one question. Yeah.
Mm-hmm. Okay. All right. I think we are running out of time, but we have last question. Have you thought about moving to augmented reality so people can still use the real hardware, do the real motions, feel the real haptic, while your instruction and advices are given as overlays? I think that's something that I had in mind as well to ask you if you have.
Absolutely. It's an excellent point. And I think so from one point of view, it's the perfect combination, right? Because you get the hands-on experience, but you still get the virtual instructions. You can still have, this structured and standardized training simulation in a way. And I think that's why a lot of research actually goes that direction. However, we again have that limitation that you need the hardware to be available to work on. And that's also, what if the hardware is actually not developed yet? What if you're trying to, learn an approach for some machinery that's not even produced yet? So we think that AR probably has more potential in terms of training outcome, but we think that it's not always actually usable for all scenarios.
Mm-hmm. Okay. All right. Thank you very much, Tiara. I think we are already over time for the questions.
Okay.
So I think we'll move on to our next speaker, but I would like to just remind the audience that if you would like to still talk to the presenters, you can do so after the talks. After the session, you can go into the hubs, or there's a Slack for the session as well, where you can ask your questions. So yeah, there's still opportunity.
I'll be checking Slack from now on.
Okay.
Thank
All
you.
right. So we'll move on to the next speaker. All right. So we'll be having our next speaker now. Our next speaker is Hemal Nayak from Max Planck Institute of Animal Behavior and also University of Constance. Hemal will be presenting some very interesting insights into animals in virtual environments. So I think without further ado, over to you, Hemal.
Hello and welcome everyone. My name is Hemal Nayak and today I'm going to present our review paper which introduces applications of virtual environments for non-human animals for the first time to the VR community. For my friends in the audience who are not sure what I'm talking about, have a look at this video. Technologies like these are developed from almost last 20 years. Such applications are used in study of animal behavior, cognition, vision, with insects, mice, and more recently, also with fish. Such applications are developed by tweaking the very same algorithms and equipment produced for creating human VR experience. However, even after 2 decades of strong work, interaction between VR community and the biologists is rather minimal. The main motivation of this review paper is to fill in this void and increase the interaction between these two communities, because there are clear advantages for both to work together. Just to give you a broad sense of how huge this community is, we had to dig into more than 35 different journals in biology to compile this review, which span from neurology, medicine, psychology, ethology, and many other topics. Therefore, this presentation will take a slightly different angle than the paper, and it will be more geared towards advantages of investing in these technologies. We study animals and their behavior for various fields of fundamental research. As it is shown in the slides here, each animal more or less shows this mechanism where it obtains information from its sensory organs, passes it on to a nervous system, and then reacts based on the information from the sensory organ and shows a behavior pattern. When we study behavior patterns, then we study this basic mechanism individually in different parts for sensory organs, nervous system, or behavior, or the whole system together as one. The findings of these studies are rather not limited to just the field of fundamental research, but often these findings are used in applied research, for example, in engineering or robotics to make autonomous robots or bio-inspired robots, and many other different kind of applications. Studying behavior requires reliable and repeatable observations. These observations are hard to make in natural surroundings with natural stimuli. Therefore, one popular method is artificial stimulation. There are different kinds of artificial stimulation: haptic, visual, olfactory, and audio. But for sake of this presentation and maintaining relevance to the community, we will stick to the visual stimuli. Biologists have used 4 different kinds of stimuli to study animals. In earlier stages, they used static stimuli, which were basically models or images which were shown to the animal, and the reaction was observed. One other type of stimuli is abstract stimuli, where the idea was to show minimum amount of features, such as points, lines, and then try to see how the animals would react to that. The third kind of stimuli used was video stimuli, in which biologists used technologies such as LCD screens, cameras, and speakers to show the animals recordings of another animals doing a certain behavior. As the technology improved for animation, graphic cards, and other kind of designs, scientists started exploring new ways of showing stimuli. One of the major advantage was that one could customize any kind of stimuli one would want, and then show different kind of animated figures or different kind of features to the animals, which would not be possible otherwise. Here in the video you can see that the fish is attacking a virtual prey which is projected on the screen of the fish tank using a simple projector. While such methods were important and interesting, they had major limitation that they were not interactive. That meant that the animals would not get feedback from the stimuli, and this would limit the study. So the scientists came up with the idea of developing interactive stimuli, which would be in closed loop. Back in the 90s, there was no tracking technology or display technology evolved to show interactive experiments. In that case, scientists designed a simple method where they connected the animal to a torque motor, which would in turn be connected to a rotating cylinder. And when the animal moved, because of the movement, the cylinder moved, and this way they could provide some kind of feedback or a closed loop mechanism for studying different kind of navigation and flying pattern based experiments. Around the same time, the VR community had already developed interactive experiments in a cave setup where a human could go inside and then see the visualizations changing around him as and when he moved the perspective. Inspired from the cave VR system, biologists built the first VR system for insects. The insects were tethered to one location to restrict its movement, and the movement was measured by a photodiode array. It was shown that the insects could well navigate in virtual spaces, and this opened completely new possibilities of studying behaviors like navigation, decision making, and even memory. Such experiments were not possible with open loop setups before. After this breakthrough, different types of setups were invented for circumventing the tracking problem. Here you can see the spherical treadmill. It was required to fix the animal on one spot, which was considered a limitation. However, this turned out to be boon for neurology experiments, where the animal was fixed at one spot and electrodes were inserted into the brain to get various neural responses while they performed different kind of behaviors. These experiments were not limited to studying insects, but soon they were extended to study mammals like mice and rats. However, the tethering and treadmill-based approaches were restricting the animal's free movement, and therefore there was a need for creating a virtual environment for freely moving animals. One of the first such environments was created from Straw Lab, where they introduced a 3D tracking system for freely moving flies and successfully displayed that flies would avoid virtual obstacles when freely moving in a 3D environment. With the help of multi-camera 3D tracking, now it is possible to track other animals and extend this freely moving virtual environment to fishes and other terrestrial insects as well as mice and rats. The virtual reality system with fish is truly unique because while the fish is tracked, the perspective is also maintained, and therefore the fish can truly navigate in a virtual environment. Not only does it interact in a game engine, but also we can see that the fish interacts with a virtual fish. After learning that animals do interact with virtual animals, now scientists at Center of Advanced Collective Behavior Studies in Konstanz are trying a novel idea. They've connected multiple such setups together in order to create a fish matrix where multiple fishes interact with each other through the virtual environment. And this is truly exciting because now we don't have to create virtual animals which interact with real animals, but we can have real animals interacting with each other in virtual spaces. Scientists from robotics community have started working with biologists since last 2 decades to create interactive robots. And now such experiments with multiple animals will give them new insights into socially behaving animals, which would lead further to create new kind of setups for socially behaving robots or multi-agent artificial intelligence. Let us have a look at some examples.
University scientists now have devised a swarm of 1,000 tiny robots that can work together without any guiding central intelligence. This is the largest team so far of self-organizing mobile robots. Working together, these robots can assemble themselves into stars, letters of the alphabet, and other complex designs. The researchers at Harvard's Weiss Institute for Biologically Inspired Engineering reported their work Thursday in Science. It is the latest innovation in the science of swarms. Swarm scientists are inspired by nature's team players, social insects like bees, ants, and termites.
Here's another example which shows that learning from insects allows us to make better machines which are more efficient and intelligent in terms of communicating with each other autonomously. Creating new kind of experiments require new kind of tracking methods. Researchers in computer vision community have also started contributing to animal behavior experiments by developing new methods for 2D and 3D tracking of not only insects but also large animals like big mammals and birds. We believe that contribution from experts in the VR community is required to push this field further. So now the question is, why should the VR community collaborate to these kind of research efforts? Well, the first reason is that animal VR, while it's sophisticated, it still lacks a lot of features, and especially in terms of development of technology. This gap can be solved by active contribution from researchers in the VR community to derive new kind of methods and create completely new kind of experiences to test different kind of scenarios. There are better ideas required for not only understanding social behavior, but also introducing new concepts like mixed reality and augmented reality. Moreover, This kind of research will put VR community in touch with a completely new community of biologists, neurologists, and other behaviors researchers which were not connected before. And this would only increase the reach of the VR community. Also, it is worth considering that findings from different insects and other small mammals could really help us understand human vision and cognition, and this would in turn help us creating better VR experiences for humans. And with that, I would like to conclude my presentation. I would like to thank you, and I'm open for questions after this video.
Thank you, Hemal. Thank you. That was
Thanks a
very,
lot.
very interesting. So we are ready to have questions, and we do have questions. So I'm going to start with the first one. A while ago, there's an anonymous question. It says, a while ago, there was a story on the news about cows in Russia experiencing VR through special HMDs. Do you have any idea whether it was it was authentic, or can you imagine such kind of work using VR?
So I've read the news about it, and I read the article, but it doesn't appear that there is any scientific backing or scientific publication. It was speculated that they put cows in VR and they feel more freer than the closed environment, but there is no reason to believe that. At least there is no scientific publication on that note.
Okay, all right. The second question is, you stated that animals interact with their virtual counterparts. Have there been studies showing that they interact with them as they would in real life, or are there changes in the behavior?
So this is what we are currently studying right now. There is not a published, so that's ongoing work in our lab right now, that we are working with virtual animals with different, so having multiple animals interact with them. But it seems that their behavior is quite real because so one reason to believe is that they usually, for example, in fishes, they have following behavior where they follow each other or they try to stick together or so on. And we do see these kind of patterns. So we are investigating it more. And also, it would be interesting for you some to know that in robotics community, they've tried having robots interact between two completely different species. So having like fish and honeybees interacting with each other through an interactive robot. So might want to check that out too. So there is some stuff happening in this field, definitely, which is exciting.
Okay, all right. And are there usually any ethical issues that one should know about?
So usually in different countries have different rules, as I understand. For vertebrates, definitely you have to follow certain ethics. For insects, I believe there is not much ethics. But yeah, you have to follow certain protocols. So definitely that is the case. And we have to go through rigorous paperwork for that.
Okay. This is a question from me. What do you think would be the next step in VR that could be helpful to the biologist? So where this gap that you mentioned that you have and which VR can fill, can you give a specific example? Is there anything in your mind that you can probably give us an example to everyone?
Yeah, very specific example is that a lot of systems, as I've shown, they've been used this cave kind of setup for a long time, but they're not able to build something more than that. So that's why in the end of my talk, I mentioned augmented reality or mixed reality kind of stuff, because there is a lot of equipment out there, but because of lack of technical expertise, these are biologists who actually learn to do coding, or some computer engineers who help transitioning these products. But usually there are no experts from the VR sector. So I think in terms of visualization, there's a lot to be discovered for how to design different kind of displays, how to show different kind of visualizations. But this all tech development takes time, because the transition between the VR and this community takes a lot. So for a concrete example, for example, in the last session, we saw a talk with multiple projectors and multiple camera system projecting fully automatic calibration on arbitrary surfaces. Those kind of things would be super useful if that is directly deployable. And therefore, it would be super nice if those researchers who are making these systems of N camera and projector fully calibration, if they would work with biologists, then that would be awesome, because then they could really create new systems. And also in terms of future, like right now in Constance, where I work, we have this new grant through which we are getting together computer scientists, psychologists, biologists to work in the same space, and creating a large space area for mixed reality, virtual reality based experiments. So large area being 15 meters by 15 meters by 8 meters. So it will be a multi-camera system with a lot of projectors and a lot of cameras, where we can track animals in real time and then show them visualization. So that's the future that we are looking at. And for anyone in the audience, I would really like to say that we are very open for collaborations. We are very open for increasing the interaction with the VR community. So would be awesome if somebody or anyone wants to collaborate with us, wants to talk about new ideas, and would be happy to feature more animal-related work in this community.
All right. Hima, there's a quick question, one
Sure.
more question. So you mentioned about now the studies that you'll be doing with animals. So here the question is, right, so far you have shown fairly small animals. Is there a reason for this? Example, studies with cats seems one of the choices that you could have. And do you think these are more difficult comparatively?
Excellent question. I think this is what paper indicates as well. It's a review paper, so we couldn't go in full detail in the presentation. But this is precisely the need of the hour, that we would like to do cats, but for that you need to do real-time tracking of cats, and that precise problem is difficult to solve, because who is going to develop these kind of tracking algorithms? So that's why a need from computer vision community is required, which was also I was showing in the last slides, that this work can come together if multiple fields. It's a truly interdisciplinary, and if only biologists work on it, they would need very sophisticated tracking algorithms, which are like deployable. But right now they are not. So if somebody is developing real-time tracking for different animals, then we don't see a reason why not to try it out. But it's difficult, since the support from the people who actually do these technologies is really less. Like, I can guarantee that there are a lot of people in the VR community who don't even know that this work exists. So that's what I would really praise one of the reviewers, that he gave us a lot of positive points on that, because this work is truly just hidden. It exists there, and I think it needs more collaboration.
Okay, yeah, that's very interesting. Thank you very much, Hema. That was an
Thanks a
interesting
lot.
talk. We will now move on to the next speaker. Before that, I would just like to remind everyone again that there is a possibility to talk to the presenters perhaps in the Slack for this session, or in the hubs as well. And we would also like to encourage people watching in hubs to turn and chat with others nearby between sessions and between papers. All right. Okay. Our next speaker is Maria Murcia Lopez from Facebook UK. And Maria will be talking about evaluating virtual reality experiences through participant choices. Over to you, Maria.
Thank you very much. So, hi everyone, my name is Maria and I'm a research scientist at Facebook AR/VR. The work I'm going to be presenting today is actually a collaboration between Tara Collingwood-Williams, William Steptoe, Russ Schwartz, Tim Loving, and Mill Slater. So I'll start with a bit of context. When developing a virtual reality application, teams typically have a choice between different configurations of the design of the system relating to hardware and/or software. Moreover, there may be trade-offs between these in terms of rendering performance, latency, cost of development, or many others. For example, avatar facial expressions that are highly accurate may be computationally expensive, but in the end make no difference to the experience of participants when compared to simpler facial expression representations. So teams building VR experiences need a way to evaluate these trade-offs. The challenge in doing so lies in the fact that we currently lack a systematic method for assessing participant experience that either does not rely on large multi-factor experiments or that is based on eliciting participant preferences across all possible configurations of a system. So in this work, we extend the previous method for evaluating presence to inform trade-offs, and we illustrate the validity of the approach with an example user study. For more context, let's just very briefly review the current approaches to evaluate presence. So currently, the standard method for evaluating it is to use questionnaires. And although questionnaires provide very valuable information, they unfortunately provide no universal measure. For example, answering 7 or at the high end of a Likert scale simply has no consequences for the respondent, but decisions that may have costly consequences for development teams may be made on that basis. Physiological measures also currently do not provide a universal solution given their complexity and utility in a limited number of scenarios. Beyond these two, there is still the problem of the explosion of conditions that is necessary to run a factorial experimental design in order to test, for example, presence across all of the possible conditions or configurations of a system. So, a method that potentially overcomes these methodological challenges was introduced by Slater, and it's actually based on an analogy with colorimetry, where to measure subjective responses to illuminated surfaces, participants are never actually asked to judge how red a color is, but only to match the perception of the color produced by adjusting red, green, and blue projectors. So carried over many participants and patches of light, experimenters can actually calculate on the average how much red, green, and blue went into the makeup of any particular color. So in their study, participants were able to manipulate different factors in order to match a previously experienced level of place illusion or plausibility illusion with all their factors at their highest setting. This allowed to calculate different probabilities on how much each of the factors contributed to either place illusion or plausibility illusion without participants ever having to answer a questionnaire. So we extend the approach and we propose an even simpler criteria for the assessment of participant responses to an application. What makes the experience better? And in this sense, whether participants prefer the experience with a specific configuration compared to others, and to what extent they would be willing to virtually pay for this configuration. So here we include a virtual budget component that restricts the number of factors that participants can maximize or invest in. And we also present an example user study, in this case, a virtual presentation, to illustrate the extension of the method. So for our example study, we designed 4 factors, each with 3 levels or alternative implementations, which are described in this table. As levels increase, so does the computational cost of the technology. All of them are variations on the facial animation system built for the Oculus Avatar SDK, and implementation details are further described in our paper. These factors and levels lead to a total of 81 possible configurations of the system. One thing I will point out is that we designed a placebo level for the eye blinking factor by having levels 1 and level 2 be the exact same technology. This was designed to test that participants would only invest in higher levels if they really made the experience better. We therefore expected participants to not invest in level 2 for eye blinking if they correctly understood and followed the task. A few more details on the experimental design. The main task was a one-to-one presentation delivered by a pre-recorded avatar. We chose this to ensure consistency between participants in the example user study. And so participants were able to evaluate factors relating to the avatar presenter. And we used Oculus Rift Consumer version 1 and touch controllers. So participants were first explained how to interact with the 3D user interface and then presented with a demo scene. This was for them to familiarize with the user interface through which they would be able to increase or decrease the factor levels. Each increase in level had a cost of 1 budget unit, and in this demo scene, there was no budget limitation. We also asked participants to think aloud during this demo and to explain to us how the UI worked, to assess that they had understood the mechanic. They then went into the first trial of the task. There were a total of 2 trials, each 8 minutes long, and at fixed points during each trial, participants were asked if they wished to make any change. If they decided to, the UI would appear and they'd be able to manipulate the factors. During the main task, however, participants were given a total of 7 budget points to spend, meaning they could only maximize all but 1 factor. Details on the mechanics of the budget system are further detailed in the paper. One more thing to note is that the order in which the factors were presented in the user interface were counterbalanced to avoid order effects. So we had a total of 55 participants take part in this example study with an average age of 35.5. 31 of them were female and 24 were male, and we also collected some information on their previous VR and gaming experience. In terms of the metrics we collected the following: transition data, or simply the chronological changes or transitions made by participants in each of the 2 trials; final configurations, which were the configurations that participants ended up in at the end of each trial; a knowledge transfer questionnaire with 16 questions about the presentation that was delivered by the avatar presenter. This was designed to assess if participants were capable of paying attention to the presentation in addition to making the transitions. We asked participants to rank the factors in order of importance, and we also had semi-structured interviews with them at the end of the session. I will present some of the results given time constraints, but the rest are obviously discussed in the paper. So from the set of all the transitions, we built a transition matrix with probabilities of transitions from configuration to configuration using Markov chain theory. We also calculated marginal probabilities for each individual factor level, and we estimated the probability of participants ending in each of the possible configurations. We found that overall, the group's most likely configuration was 2111, which is highlighted in this table. Note that in this configuration, the budget is not maximized. There was a total of 7 units to spend. However, to reach this configuration, you only have to spend 5 units. This is valuable information for teams who are developing and implementing this technology, as it helps us understand where degradations to the different factors may actually be acceptable in the experience. We also found no significant difference in the final configuration distribution between trial 1 and trial 2. Going back to the placebo effect for the eye blinking factor, which is the one highlighted in this table, if we focus on the area that covers after 7 transitions, which was the maximum allowance of changes for participants, if we focus on level 2, which is the one where the placebo was available, we actually noticed that the probability of selecting that level was very low. This helped us validate that the task had been understood by participants. To clarify, participants were asked to only spend budget if it made the experience better for them. In terms of budget, the mean budget spend was 4.7 out of a total of 7. And we found no statistically significant difference between trials, gender, or gaming experience. This was important for us as it suggested that there is a point of equilibrium that did not simply imply maximizing all factors. And this is in line with the theory denoted in previous uses of this method. The time taken to complete transitions decreased over time, and we saw no significant differences between the 2 trials. We believe that this could be related to the fact that towards the end of each trial, participants may have already found their optimal configuration or settled on it, and it could also relate to fatigue or participants simply wanting to end the task earlier. In terms of the knowledge transfer questionnaire, we found In general, high scores across most questions except for 2 of them. So we found that the questions with the lowest correct responses, which are question 1 and question 8 highlighted in this graph, corresponded to the facts that were delivered at the beginning of each trial in the presentation. And this suggests that participants may have been settling into the experience and paying less attention to the presenter. However, overall, given the results are pretty high, we are confident that people were able to follow the presenter as well as perform the transitions over time. In terms of interview responses, we coded them into a number of themes. Here are some of them. Participants actually felt they had sufficient opportunities to assess the factors and also believed that the configuration they ended up in was the best one given the available options. This was important for us to check given that there were limited opportunities to make changes over time. Participants also told us that the budget was sufficient to find a match. This is in line with the previous results I showed on how much budget people spent. And one thing we were really interested in was asking participants what their goal was as they were trying to make the experience better. So participants told us that they were aiming to make the presenter more real, more natural, not mechanic, human, less distracting, more comfortable, and more lifelike. These are actually words that are often used to describe social presence. So this work extends the previously used methodology by introducing a novel application of a virtual budget concept, using a placebo to validate the design, proposing a new goal for participants to make the experience better, where they no longer have to match a previously experienced sensation with all factors at their maximum level. And also, we allow participants to move between configurations in any direction, therefore removing the assumption that a given level of a factor is better than another. There are still a few limitations with the approach. On one hand, we don't know to what extent the results from the study would generalize to other scenarios. We also don't understand what's the maximum reasonable number of factors and levels for an evaluation using this method. Obviously, the higher the number of factors and levels, then the larger the Markov transition matrix that has to be populated with data. And also the higher the cognitive workload for participants who are making assessments over time. Another limitation is that it relies on one particular analytical technique, which is Markov chain theory. However, there may be additional ways to approach the analysis that could yield novel insights. In terms of future work, we encourage the following: to explore other applications, extending the range of use cases we evaluated. So it'd be interesting to see if, given a different task, participants would have reached the same conclusions. To study individual differences, even though our goal was to model the average user based on the actions that participants took, it'd be interesting to study individual differences. We should explore other budget restrictions that will force participants into tighter evaluations, or conversely, scenarios in which the budget allows for the maximization of all the factors to understand whether a point of equilibrium can still be reached when there is no tension. And most importantly, the budget could actually reflect real costs, for example, of implementation or production. We should try different configuration starting points for the trials, such as completely random or configurations with high levels. In this particular study, we started with all the levels at 0, except one of them being at level 1. And it'd be interesting to explore whether we can reach consistent points of equilibrium despite different starting points. And interestingly, we believe this could be run in the wild by embedding the experience in public applications and optionally allowing headset owners to take part in them. So this is everything I had. I want to thank Tom, Tash, Sim, Kush, Victoria, Max, and Jessica for their contributions to this work. Thank you very much.
All right. Thank you very much, Maria. We are now ready for questions. If anybody has any questions, I do have one question. So actually two. So first was why in particular did you choose? Was there a reason you chose eyesight as the factor for placebo?
No, it was almost a random design choice. We wanted to do it on one of them, and that was the choice.
Okay, all right.
Yeah.
And right now, all the factors that you chose, it seems that they were very relevant for a social VR environment. Do you think this could be extended, the same factors, or perhaps the budget could be the budget restrictions could be applied to other factors and other applications? Do you think?
Yes. So, oh yes, sorry. We actually built this tool as a way for us to evaluate different systems that we're building at Facebook. And this framework has already been used following this work on a number of scenarios, some of which don't even relate to VR. So we actually found that it's pretty powerful. And as long as you can frame the research question under this factor level sort of setting, it can be applied in many different contexts.
Okay, we have two more questions. One is that I think it was missed by one of the audience, that what exactly were the instructions that you gave to the participant? That is, what constituted a match?
Yes, so we obviously settled participants into the task. In this particular case, we told them they were going to listen to an avatar delivering a presentation. And the specific goal we gave them was to only spend budget if it made the experience better for them. Participants knew that they would have certain number of opportunities to make changes. And when they reached the final opportunity, they would have to confirm their final selection in a dialogue. So that way they were confirming the setup they were in.
Okay, all right. And the last question is, do you think that your method could extend to make a personalized avatar for self-embodiment?
I think so. So this same method conceptually can be applied, as I mentioned earlier, to a number of scenarios. So it'd be really interesting, for example, to place people in front of an avatar configurator as an example, right? And to see how they proceed to make changes over time. What's interesting about this method is not only where people end up in, which is very valuable, but also how they change over time. So it'd be interesting to see, for example, if people choose to change their hairstyle before changing their clothing, or other sort of patterns that we might observe as to how people make these configurations over time.
Okay, all right. Thank you very much, Maria. I think we can end this talk now, and we would then move over to the next talk. I just want to remind everyone again that you can talk later as well after talk in this Slack for this session or the hubs. Okay, we will now move on to the next session, and we'll be transitioning soon. Okay. All right. So thank you very much again for waiting for us for the transition. Our next speaker is Yun Sean Pai from the University of Auckland, New Zealand. And Yun will be talking about measuring human trust in a virtual assistant using physiological sensing in virtual reality. So over to you, Yun.
Thank you very much, Janki, for the introduction. So once again, my name is Yun Suen Pai from the Empathic Computing Laboratory, and I'm a postdoc. And right now I'll present our research entitled Measuring Human Trust in a Virtual Assistant Using Physiological Sensing in Virtual Reality. So just sit back, relax, and enjoy. I'll start off with a brief introduction for our research. I'd like to mention a little bit first about cognitive load. So cognitive load is about the working memory. And in our work, we're trying to understand its correlation with trust. And interestingly, it has been discussed before that cognitive load, when interacting with the devices, machines, or computers, largely depends on how much we trust that particular machine. Through an economic trust game, Sampson et al. Showed high trust-based impulsive actions when there was less or no cognitive load, which was interesting. They also displayed less trust, as in the people displayed less trust when their cognitive loads have increased when interacting with devices or computers. So after the introduction, I'm just going to go through some little work, just going to highlight some work relating to the studies on trust and its correlation with cognitive load. So in some of the past works, researchers have used EEG and GSR to use as a measure for a physiological measure for trust. For example, Akash used EEG, electroencephalography, and galvanic skin response, GSR, to measure human trust towards machines. When they were driving in desktop, so it's not a VR setup. Salinity also demonstrated that presence influences trust in a VR task. However, they only used a subjective measure for this, so just use a questionnaire. Looking towards the correlation between trust and cognitive load, Kawaji suggested that galvanic skin response is a useful tool to measure the interpersonal trust for both low and high cognitive load tasks. However, he used a desktop text chat environment, and it's also between humans, basically, it's not with the machines. Gupta explored the correlation between physical signals of trust and cognitive load in VR, and did find that the average EEG alpha band power correlates with a voice assistance depending on the cognitive load conditions. However, they did find that the task that they used was, firstly, it was a combination of a NBAC task, which is a well-known physiological test, it's a well-known test towards measuring cognitive load, as well as a ship selector task in virtual environment. So they just combined these two tasks together separately, and they found that the task wasn't as hard as it was supposed to be. So this is some of the little work that I'd like to stress upon. There's a lot more that we explored in our work, actually. They are available in the paper, but for now, I'm just going to summarize this in this table right here. Where our method differs is that we developed a VR environment which integrates this NBAC task into a shape selected task. So our previous work was separated. Here, in this case, we combine it, and we try to induce 3 kinds of key cognitive loads and to understand its trust towards a voice assistance that will be guiding you in the task. So through our research, we will be presenting a custom VR environment meant to maximize or minimize cognitive load in the presence of a reliable or unreliable virtual agent. So we'll have 2 independent variables here. We explore the relationship between the agent trust and induced cognitive load based on gathered physiological signals, behavioral aspects, as well as subjective feedbacks. So 3 key results, 3 main results in terms of the physiological, behavioral, and subjective. And finally, we found that the EEG alpha channel and the frequency domain mean power, peak frequency for galvanic skin response, as well as total power spectral density, specifically 0.05 Hertz as well as 0.12 Hertz, the rounds completed per seconds, as well as the subjective questionnaires that we employed to be indicative of the user's trust in different cognitive states. So I'll now move on to the system design. So for our system, we use the OpenBCI EEG cap with 16 electrodes. We also use the OpenBCI GUI to stream the data out. We use the shimmer sensor for the GSR as well as heart rate variability signals mounted on the user's left hand. Maybe I could enable my laser pointer over here. So this is the GSR sensor. And we use a Java application to stream the shimmer sensor signals outside towards a Unity 3D game environment, which we developed for the shape selector task. Everything using a first generation HTC Vive HMD for the participants to view the environment. So this was modified from our previous research work, which was published in VRST 2019. So in this task, we separate between a primary and a secondary task. For the primary task is the shapes selector task, where the user is supposed to look for a target object around them. So it's always placed all around them with different shapes and different colors. So their target object can be seen in this yellow background, pink background over here. So if they are meant to look for a blue cube, for example, they have to look around, and once they find a blue cube, they just select it. But all this while, the secondary task plays at the background. So while they're selecting for this object, they have a ladder at the top here that keeps flashing every few seconds. So this is the NBAC task, actually. So for NBAC task, it's about memorization. So when a letter appears here, for example, B, and then later on, we'll ask you what was the letter that just appeared before, and then you have to select B, for example. But that's for 1 back task. If it's 2 back tasks, then you need to memorize 2 letters before. So while selecting the shape selector, the user must also keep an eye towards the letters that are appearing at the same time. So by designing a task like this, it induces all kinds of cognitive loads, namely memorization for the NBAC, multitasking where they have to skip between the primary and the secondary task, as well as temporal load, because between the high and low cognitive load, we use either 10 seconds or 5 seconds to complete the task. So they're only given a short amount of time. So it's not all that hard because we have a voice assistant to actually help the user to select an object for their primary task. So since they need to look around the environment to select for the object, there's a voice assistant telling them to either look left or right. So it always updates depending on where the user is currently facing. For the low cognitive load, for the low accuracy of the voice assistant, we set it to 50% accurate. So it's pretty much random. It doesn't lean towards accurate or not accurate. Whereas for high accuracy, it will be 100% accurate. So it'll always be correct, basically. If the object's to the left, it will be at the left. If it's 50%, so it could be lying. It's basically random. Once again, for the devices, we use the OpenBCI EEG cap with the Cyton Daisy chain module, which samples at up to 125 Hertz, 16 channels. We place electrodes at the prefrontal, parietal, and occipital lobe of the user. As for the Schirmer sensor for measuring GSR and HRV, so galvanic skin response and heart rate variability, it samples at 128 Hertz, and all this is streamed into a Unity environment displayed through the HTC Vive VR head-mounted display for the VR environment, and to also enable interactions. So we take some safety measures. We can see in this image over here. Let me just enable my laser pointer once more. So you can see that we tried to minimize motion artifacts. Actually, we had to strap the left hand, which is the left hand of the user, which has the GSR sensor towards the backpack resting around their shoulder, actually. And whereas we have the entire cable of the HTC Vive wired upwards, so there was no like pulling towards the HMD while they was wearing to avoid any displacement in the EEG cap. So now I'll move on to the user study. We designed a 3x2 within subject user study on 24 participants, where 50% of them are female, age mean 28, and a standard deviation of 3.1. So it's a 3x2 study with two levels of accuracy, actually, but we have a no voice assistant, we have low accuracy voice assistant, as well as high accuracy voice assistant. And as for cognitive load, there's low and high cognitive load. So the no voice assistant is more like for baseline. In terms of the obtained results, so for the physiological signals, there's the EEG signals, electroencephalography, skin conductance or galvanic skin response, and finally the heart rate variability. For the behavioral trust measures, we look at how the user turns around. So we always logged their turning direction towards the left or towards the right whenever they hear the voice telling them to go left or right, to turn left or right, as well as their player performance, as in the amount of rounds they managed to complete given the amount of time that we allocated to them, which I think is about 7 minutes per session. And then we have also subjective measures, which are questionnaires. We have them fill up the NESA TLX, task load for cognitive load, the system trust scale for the perceived trust, and finally the subjective mental effort questionnaire. I'll now move on to the results. So from our study, we found that there was a significant main effect of cognitive load on the alpha band power. So from the EEG signals that we gathered, we only extracted the alpha band power from the related work, and we found that there was some significant effects. Looking at the descriptive analysis of the average alpha band power, there was also a 71% decrease in the alpha band power from the low to high cognitive load for the low accuracy, and as well as 27% increase in the alpha band power from low to high cognitive load for the high accuracy voice assistant, which is actually in line with previous work because actually the EEG alpha band power is inversely proportional towards the cognitive load. As for the GSR signals, we performed the FFT analysis, and we found that the mean and peak frequency significantly differs across different levels of trust. One interesting finding that we found is that there was a significant main effect of cognitive load on the total power of the FFT at approximately 0.05 Hertz, as well as 0.12 Hertz. So we think this is rather interesting. I think there's been some related work that we cited in the paper saying that this range has some correlation towards the cognitive load, and we found that 0.05 Hertz and 0.12 Hertz to be significant. However, when looking at heart rate variability, we did not find any significant main or interaction effects towards the results. But looking at the descriptive analysis of the low to high frequency ratio, which is a common feature used for heart rate variability analysis, 24% increase in mean from the low to high cognitive load for no voice assistance, 20% increase in the mean from low to high for low accuracy voice assistance, and finally 2% decrease in mean from low to high cognitive load for high accuracy voice assistance. Looking at the behavioral measures, so as in the head movements and the round per second, for the head movements, we didn't find any significant interaction effects, but we did find a decrease of by 4% in high cognitive load compared to low cognitive load between the different voice assistance accuracy level, as well as an increase by 0.7% in high cognitive load compared to low cognitive load by looking at only the high accuracy of the voice assistance. Looking at the round per second, though, we found that there was a significant main effect towards the accuracy of the voice assistance, or the trust towards the voice assistance. Looking at the subjective measure, so for the system trust scale, so all three questionnaires showed significance, where the system trust scale shows a main effect in accuracy and cognitive load, as well as the interaction between them. The Nesta test load shows a main effect in accuracy as well as cognitive load, as well as the subjective mental effort questionnaire, which has the main effect towards the cognitive load. So I'm going to go through the discussion right now. So we found that overall, for the EEG, the alpha band power was indicative of the user's cognitive load, which was in line with previous related work, because the reduce in alpha band power indicates an increase in physiological cognitive load. For the GSR signals, there was an amplitude from total power analysis at 0.05 Hz and 0.12 Hz, which reflects this cognitive loads in relation to different trust levels. For heart rate variability, there was a decrease in mean, even though there was no significance, but we do think that is good for future works. As well as for inaccurate agent, it means that the LFHF ratio increased even for conditions with no agents. Some interesting feedback that we got from participants is that they feel that the voice assistant helped make the job easier, but they would actually prefer to not have any voice assistance if the helper is inconsistent. So compared to low accuracy voice assistance, it's even better to not have one at all, because it probably just confuses them. A very interesting feedback that we got is that some of them actually take the direction given by the voice assistant as a form of heads up. So even if it's right or wrong, they'll just follow it, because if it's correct, it's great. Otherwise, there's a 50% chance that it's wrong and it just turn the other direction. So which is why we didn't get any significance for the head turning. But the rounds per second in high accuracy was significant, because when the voice agent was reliable, then they managed to complete more rounds because they relied on it. And in high cognitive load and low accuracy voice assistant conditions, 3 participants started following the opposite to the suggested directions, because they simply do not trust the voice assistant anymore. Okay, so in conclusion, we found that so this is a list of things that we found out from our results, which is the EEG alpha channel, the frequency domain mean power, peak frequency, and total power spectral density, or GSR, at 0.5 and 0.12 Hz, the rounds completed per second, as well as all 3 subjective questionnaires to be indicative of the user's trust and cognitive load, and we find them to be useful parameters. And overall, we introduced a novel methodology for exploring correlation between physiological signals with trust and cognitive load using VR as a medium or as a platform for evaluation. For our future works, we will be expanding the sensing for more physiological signals. So we'll look at EMG, electromyography, or muscle sensing, eye tracking, and so on. We'll look more towards a machine learning-based approach for real-time trust detector using real-time signal processing. And finally, we'd like to investigate any relationship between cognitive load and trust using other EEG bands. So right now, we only explore alpha bands, but I think other bands should also show some correlations, delta, theta, beta, and gamma. So we plan to look to those as well for the future works. That brings me to the end of my presentation. Once again, I'm Yoon Sun Pai. Thank you very much. And now I'm open for questions.
All right. So thank you, Yoon, for the presentation, and we will now take the questions. The first question is, how exactly did you stream the OpenBCI data to C# scripts in Unity?
We use a lab streaming layer, LSL, though in actuality, you can use any protocol that you want. We tested several and we just found LSL to be a little bit easier. And because I think Shimmer also directly supports LSL, so we just relied on that to stream towards the Unity C# script.
Okay. And can you differentiate between trust and cognitive load from GSR data?
That's actually a slightly difficult question to ask, and I'm glad you asked that, because we found a interaction effect between the accuracy and, the trust towards the different levels, the two levels of voice assistance, as well as the varying levels of cognitive load. So we have proven that the GSR signals does actually show strong correlations. However, it's hard for me to tell you right now that if the GSR could actually be like more significant towards trust or cognitive load. So we keep some of these for the future later works, but I can tell you right now that at least at what we've established is that at this 0.05 Hz and 0.12 Hz of the FFT spectrum, frequency spectrum of the GSR to be indicative of this both trust and cognitive load.
Okay, and I missed a part of your last slide actually. I don't know if you mentioned, did you mention that you would be also considering eye tracking? Because I think that would have been interesting as well too.
Yes, so eye tracking is definitely down the pipeline. We didn't include that because there was really enough sensing for us. So we also explored EEG, skin conductance, and heart rate variability mainly because of related work. But they're saying that there's also a lot of related work on using eye tracking. So we plan to explore that in the future. Though one of the issues, or at least one of the challenges that we have faced previously for the signals that we have chosen is actually the pre-processing and the noises that comes with them, especially motion artifacts. So this is something that eye tracking would have a little bit of a leverage or benefit compared to the rest of the signals that we've collected actually. So it's definitely something that we plan to explore in the future.
Okay, all right. And just one thing that I remember when you mentioned the title actually of the study, I once came across a paper which explored the neural correlates of trust, and within that they had they presented users with trustable faces and non-trustworthy faces as well. And right now, when I look into what you are looking, maybe do you think it would limit to certain kinds of applications when you are trying to measure trust in this way, or because there are certain other factors as well that might, I was just, it just came in my head because if I look at someone and I don't trust them, and it's nothing to do with cognitive load.
Yeah, I agree with that. So there are many factors that influence trust, obviously. We're just limiting it for our study scope. But from some of the things that we found in the past, it's true that how someone looks, how someone sounds, you know, how the avatar is designed, or you know, I'm not to be racist or anything, but skin color is also affected. So there's many things that affect our perceived trust towards the person. So we try to make sure everything. So one of the reasons why we use voice assistant, because we didn't want an avatar to appear. Otherwise, you judge how the avatar looks. So we did use a female voice assistant for this because we tried to get a genderless voice assistant initially, but that didn't work out. It was difficult. So we relied on the female voice assistant. So that could have some effect on the results actually, because we have 50% female or male. But when we did analysis, we didn't find any effects of gender. So we didn't include that. But that's an interesting question, and definitely should be explored in the future as well. The effects of virtual avatar appearance, sound, even the environment itself actually could affect trust. So
And you had half of the participants female and half of them male. Did you see any differences in there, or have you looked into it yet? No.
Yeah, we did. So there was no difference in that.
All right. Okay. Thank you very much, Yun.
Thank you very much.
All right. So we will now be moving on to our next speaker, and we will shortly be transitioning to the next speaker. So just be patient with us. All right. All right, welcome back, everyone. Our fifth speaker is Fabian Greskoviak, who is a PhD student in the Rainbow team of INRIA, France, and with an objective to design navigation techniques for robots in crowded environment. Fabian will be presenting their work on virtual reality-based evaluation of robot navigation among people. So over to you, Fabian.
Hello everyone, my name is Fabien Greskoviak. Let me present my work entitled Evaluation of Robot Navigation Among People, which presents an original use case of virtual reality. This work is part of the European Edge 2020 CrowdBot project. The CrowdBot project was built to address the freeze robot problem, formally described by Troutman in 2010. Robots, such as this delivery robot, are expected to perform safe navigation potentially very close to moving people. In such cases, robots will have to stop as soon as an imminent collision hazard is detected, taking into account human motion prediction uncertainty. Once the environment surpasses a certain level of complexity, any path will be considered unsafe and the robot freezes in place. Since a feasible path typically exists, this behavior is suboptimal and might lead to dangerous situations. For instance, the robot might block an exit door during an evacuation, which is not acceptable. In order to solve this issue, it is necessary to improve the precision of the human motion prediction, as well as the motion planning of the robot. To assess the planner performances in situations of near collision, an evaluation protocol taking the presence of humans into account is required. In the literature, for instance with the frozen planner, the method of evaluation consists in performing real conditions experiments where the robot is in the crowd. Such real conditions experiments might be difficult to perform, especially if the robot is heavy or bulky, or moves with a lot of energy. For instance, with this security robot, which weighs 136 kilograms, near-collision human-robot interactions is hardly doable in experimental conditions without raising ethics issues. Another example is the experimentation with autonomous buses, which are powerful, thus dangerous in crowded environments. To evaluate robot behavior, it is possible to use a simulation instead. For instance, in this video showing the CrowdBot simulator, a simulated robot moves through a simulated crowd. The main issue is that human reaction to robot is really difficult to capture when using a simulation algorithm. Similarly, the robot sensing capabilities, its information processing capabilities, and mechanical behavior is hard to capture. In the end, a simulation is quite limited in its capacity to simulate human-robot interaction, and a real condition experiment is always required. To keep the safety brought by the simulation and the realism of real condition experiments, our idea is to use virtual reality to immerse both a human and a robot to create a virtual interaction. The use of virtual reality for robotics application is not new. For instance, this collaborative robot is being controlled by an operator using virtual reality. However, to the best of our knowledge, no human-robot interaction studies involve both the robot and the human fully immersed in the virtual world. Our proposition is to use virtual reality in a way that the realism of the interaction is kept intact and no simulation of the robot nor the human is required. In addition, we have the usual benefits of virtual reality, that is, keeping control over the experiment regarding the data conduction and repeatability. Finally, we guarantee a safe and collision-free experience during near-collision human-robot interactions. The main novelty in our work is to immerse together the human and the robot in the virtual environment. Immersing a human is usual here, but immersing the robot will enable us to keep the realism of its way to sense the human motion, and the way it reacts accordingly. It allows us to use any robot without the need to model it. It allows the robot to interact with the virtual world as if it was a real world. Our first contribution is a new use of virtual reality to immerse a human and a robot. Our second contribution is a pilot study to assess our VR platform capability of delivering non-biased experimental data. There are 3 workspaces in our platform: a physical participant workspace, a virtual interaction workspace, and a physical robot workspace. The physical participant workspace is the place where the participant is present, alone, and is allowed to move freely without the risk of collision. In this place, the participant's body motion is tracked and broadcasted to the virtual interaction workspace. In the virtual interaction workspace, an avatar replicates the human participant motion in real time. The third workspace is the physical robot workspace. It is the place where the robot can move without risking collision with humans or obstacles. Again, the robot motion is tracked, and motion data is broadcasted to the virtual interaction workspace. This virtual place, where the participant avatar already is, now also have a robot avatar which replicates the robot motion. Now, in terms of perception, the virtual interaction workspace is graphically rendered from the point of view of the human avatar and displayed to the human using a HMD. Doing so, the participant can perceive the robot motion in the virtual place. Concerning the robot, its sensors are simulated in order to perceive the virtual world as if it was a real world. This figure shows the technical complexity of the platform. You can retrieve the same workspaces I just described, formally described in the paper. This figure shows the different components we used for the pilot study: the tracking systems, Vicon and Xsense, a FOV HMD, the robot Pepper, and the sensors we simulated, and how everything is connected. In the end, while the robot and the participant are physically separated in their respective workspaces, they perceive a virtual interaction as if they were in close proximity. Our second contribution is the pilot evaluation of the bias in human-robot interaction experiments performed in virtual reality. Our objective is to find out if data collected during near-collision human-robot interaction experiments are biased due to the system I just described. The objective is ambitious, thus we decided to remain very simple and run a pilot study with 2 simple tasks. First, our robot is moving in a sinusoidal movement, back and forth. Participants were asked to follow the robot. In the second task, participants were asked to lead the movement and move back and forth. Both tasks were performed using virtual reality or in real conditions. I now present a trial of the study to illustrate the tasks and conditions. First, the robot leads the interaction in real conditions, then with our virtual reality platform. Second, the human leads the interaction in real conditions. Then with our virtual reality platform. To evaluate our system, we used the robot Pepper, a humanoid robot which is lightweight and moves slowly, thus is safe to use with participants. For the robot to be able to perceive the virtual environment, we had to simulate some of its sensors: the front camera, the 3D sensor, the laser sensors, the infrared sensors, the sonar sensors, and the bumpers. For this study, our hypotheses are: in virtual and real conditions, the trajectories of the participant and the robot will be highly correlated over time. The virtual condition will induce a higher reaction time from the robot and the participant than the real condition. In the virtual condition, the human speed will be lower than in real condition, as it is a commonly observed fact. For the results, the first hypothesis was that in virtual and real conditions, the trajectories of the participant and the robot will be highly correlated over time. To evaluate this, we used cross-correlation. In signal processing, cross-correlation is a measure of similarities of two time series as a function of the displacement of one relative to the other. On this example, the time series G is being delayed up to a point where the time series F and G are the same. This gives us the higher correlation associated to a delay corresponding to the displacement of the time series G. What we found is that for each trial of each task, in each condition, the trajectories of the human and the robot were similar to the example trial shown here, and were highly correlated. For instance, in the example here, the correlation was 0.95. We expected a higher reaction time in virtual reality. The computed delays are part of the cross-correlation results. We find that for the task 1, where the robot leads the human follow, the delays are close to 0 in real condition as well as in virtual condition, which contradict the hypothesis. We explain this by the fact that the robot paper was moving slowly and the participant had plenty of time to follow the robot motion. We also believe that the repetitive motion helped the participant to anticipate the robot motion. The second task, where the robot follows, shows slightly higher delays in virtual reality than in real condition, which goes in the direction of our hypothesis. We think that the two tasks have different results because the participants anticipated the movement, while the robot was not capable of doing so, and was purely reactive. For the third hypothesis, we expected that the human speed will be lower in virtual conditions than in real conditions, as it is a commonly observed fact. We find that we cannot conclude for the moment. The difference in speed between the two conditions was not significant. Also, we noticed that the robot was moving faster in the virtual reality condition than in the real condition. The graph represents the average speed of the robot for the task where it leads the motion. In blue, the task is performed in virtual reality, while in red, the task is performed in real condition. While the two curves should have been the same, the blue one reaches higher velocity. We believe this is due to two factors. First, there was probably a calibration error of the robot sensors. Second, the robot paper has limited speed capabilities and is a lot slower than the average human pace. To conclude about our work, we designed an evaluation platform for near-collision human-robot interaction that is safe by design, and it preserves the human-robot interaction. With our method, no human or robot models are required. Finally, it is adaptable and generic, as it is compatible with any robot, any tracking device, and any head-mounted display. Concerning the pilot study, we noticed limited perception bias. In the end, the study merits further investigations. Our future work will be twofold. First, we plan to improve the immersion of participants thanks to additional devices for haptic rendering and sound rendering. Second, we plan to perform full experiments dealing with near-collision human-robot interaction. Our idea is to have a human following a robot closely in a virtual crowd, and to analyze the interaction during events when the robot performs unexpected actions such as brutal stops. Thank you for your attention.
All right.
Hi.
Thank you, Fabian. That was an interesting talk. We do have some questions already, but we are ready for more questions. So if anybody else have questions, please fire away. The question is, how do you simulate the sensors of the robot, and perfect sensors, or is there a realistic noise? This is what one of the audience wants to know.
So to simulate the sensors, we implemented some noise, so Gaussian noise, spikes, or offsets, and actually it depends on each sensor. For instance, if you take the RGBD camera, you will have mainly the noise coming from the compression of the image coming from Unity. But for the other sensors, for instance, sonars, you'll have Gaussian noise, spikes, and maybe offset. It depends on each sensor.
Okay.
I hope.
Okay. And the next question is, can you talk a little bit more about how you hope to use wearable haptics in your future work?
Yeah, sure. So we are currently working on some devices and trying to find out if they are useful for people to use to move in a crowd. So if those devices appears to be efficient, then we would like to use them as a tool to immerse even more our participants in our simulated crowd.
Okay. All right. Just one quick question, Fabian. The second hypothesis about the higher reaction times, I missed some part there. Why do you think there were higher reaction times in VR?
No, what we expected is that the higher reaction time because of the whole system and latency induced by the system. Because in real condition, well, you don't have any latency. You directly interact with the robot or the person. But with the system, we expected, as it is like a network of a lot of things connected together, we expected some maybe latency.
Okay.
Yeah.
The next question is, was there also the noise of the robot, for example, when the robot is moving, driving, auralized in VR setting or the VR application, or was it only the visual sense that you have integrated in? So how realistic was it?
No, it was actually yeah. So it's one point of the conclusion is that many participants were annoyed by the noise of the robot. The real robot actually. So yeah, in the virtual reality, the noise was not rendered. So yeah, that's definitely a major point of improvement of the system for the actual experiments we run with it.
Okay, all right. Thank you very much, Fabian. I think that was our last talk of the day. And I want to thank everyone We have reached to the end of the session. I want to thank all the participation from the audience and the presenters, of course. It has been interesting talks and very interesting experience in the virtual conference. And just a reminder, you can head over to the hubs after the break to join the 3D UI contest and the research demos as well, which is the next after this. And the general chairs have also put a bunch of hub rooms marked sponsors and social, and you can always consider popping into there and the social rooms between the sessions to thank the sponsors or just to meet each other or chat. Yeah, I think that's it. I also want to thank everyone in the background, our coordinator, Catherine, for making everything work so smoothly. And I wish everyone a good day wherever you are. Stay safe.